Thanks everyone, and welcome to the talk. Yeah, the talk is about stateful functions on Apache Flink, but I'll try to talk about it in like not necessarily purely tied to Apache Flink, but more like some thoughts on like I think you can say the intersection of the stream processing ecosystem, serverless architectures, and just building event-driven applications nowadays. And I need to start with a disclaimer here that I'm very honored to be giving this talk about this project. This is, in fact, actually in a pretty early stage open source project. I think it started like towards the very end of last year only. And most of what I'm presenting here, like design choices and so on, have not been validated in the way we used to do this when we were, doing academic research or so, doing rigorous benchmarks. But they were mostly validated by, just by applying actually user workloads and problems to them. And that's not saying that we're not interested in any academic evaluation. In fact, we'd be very interested. So if you find what I'm presenting here interesting or maybe relevant to parts of your own work, I'd be definitely interested to talk about, if there's ways to collaborate on testing or evaluating some of these ideas here a bit deeper. Okay, so yes, the talk was announced as stateful functions on Apache Flink, but maybe an alternative title that almost describes this talk better would be an excursion of a stream processor into the world of applications and microservices, because that's in some sense what this project is about, trying to apply the ideas of state management and messaging to the world of distributed applications, distributed microservices, and so on. And parts of this work were actually motivated by something like this. So this is a very very non-scientific motivation, but in some sense describes part of the state of industry or working with certain users pretty well, right? There's this trend of very, very powerful infrastructure that we're having these days, driven by cloud providers, driven by projects like Kubernetes and so on, and somehow everybody assumes that just solved all the problems out there. And bit by bit, folks do actually find out that putting something in a container in Kubernetes is not by itself a solution to any application architecture. It's basically a deployment or an orchestration tool, an infrastructure tool. It doesn't really solve for you building a distributed application in a good way. And that part is actually still surprisingly hard. And that's what this project is trying to do, trying to ease this distributed application development with the help of some ideas from stream processing. And there's some very simple problems that we can look at that actually motivate at least parts of what this project is doing. So if we take the very simple example of just a few microservices interacting and looking, how most of this is done today, or and what problems people still have to solve repeatedly again and again and again. So let's take this simple example here. 1 second. All right. Yeah, that's the right one. Let's take this simple example here. We do have, let's take this as 3 different microservices. They follow this classic tiered architecture. There's some application logic that's invoked by a request coming, let's say, through an API gateway. This is, let's say, using a bit of the terms if you're building this on, let's say, on a cloud with something like functions as a service or so. You probably recognize the Lambda here also being a reference to that. So yeah, let's take this as an example. We have a few services built as as functions or a stateless application layer, and some databases. And a request comes in, the functions do their usual application logic handling of the request. They do talk to the database. Maybe it's a key value store and it's just some get and put request for individual rows, or it's a slightly more complex SQL query. And then they talk to other services by making RPC calls or putting some events in a message queue. And when a lot of this interaction is typically driven by the application layer, pretty much in all cases. So the request comes in, there's maybe some updates to the database state, and then an RPC call to the next service. And that next service also does something with its database, and then it goes on. And if this, let's say this RPC call between these applications fails, then we're actually in a bit of a tricky situation immediately, because now how do we deal with this? It's of course possible to deal with this, but it's a problem that pretty much every application is still solving again and again, because it's still tricky to determine what's the best way to deal with this. After all, we don't quite know. Did it actually go through? Did the target service materialize something and we just have a network issue? Did the request actually not go through? Should we roll back any local interactions and so on? And yeah, this it's one of the problems that many application developers actually solve time and time again every time they're building an application. Of course, there's solutions to that. It's not that it's an impossible thing to solve. The theoretical problem of did the message arrive or not is actually not solvable. This is this famous two generals problem, and this also, I think there's a lot of misunderstanding about that, because for a lot of folks that actually draws the conclusion from my observation that you shouldn't even try to do anything in this space. But we're not really interested in the fact whether a message arrived or not. We're mostly interested in the fact of whether the message was communicated, or not whether it was communicated exactly once, but whether some effects that are from the message were materialized consistently. And that, of course, is a solvable problem, right? The database community has been doing this for decades, and there's all sorts of approaches to that. Simplest one is if your operations are idempotent and you just retry. If they're not, there's various protocols for distributed transactions, for undo workflows and so on to make sure everything stays in sync. And there's still it's still a bit of a problem though to apply this in practice, because let's just assume we do actually want to do this. We do want to provide some way for applications to not worry about this and just say like, yeah, you do your database operations, you send out your message, and it either both works or not. So we're trying to basically do this transactionally. And let's simplify this just to the problem of this one service making a change in one database and putting a message in a message queue. And even that is in practice often a bit of a problem, because the message queue, the database are separate services. So we do need an external transaction coordinator to deal with that. The database and the message queue would both have to coordinate with that external transaction coordinator in order to decide to commit or abort their transaction. Transaction for the database meaning commit the change to the state. Transaction on the message queue would be commit the message being enqueued. But yeah, so if we want to run this in one transaction, there are attempts to do this. It gets surprisingly unwieldy in practice quickly to do this. But it sounds like it shouldn't be so hard, really. And so one simple trick that actually simplifies this problem immediately is, what if the database was actually also a message queue at the same time, right? Then we basically have one system that we talk to, that everything that kind of involves stateful updates being, queuing a message in a message queue, it's kind of a stateful update. Making a change in the database is a stateful update. What if we could just do this with one system, and then it would be extremely easy to also implement this as one transaction, and quite efficient. And yeah, this is kind of, I think, already one of the main directions of this talk. Like, what can we do in practice to actually exploit this idea a bit better? So basically, run it as one transaction, just through the database. And here's a little thought experiment to maybe take this a step further. It's really completely reversed these roles of the database and the application in terms of who's actually driving the updates and the messaging and so on. Let's say traditionally we have this case that the application drives the whole thing. With input events coming in, they kind of come in through a message queue or through an RPC call, and then the application talks to the database and produces some result messages or result RPC calls. It really applies in all cases. What if we could flip this around and actually say all events that come in, they actually come in first in the database? Maybe the database even knows how to co-locate these events with, let's say, a bioprimary key with a partition that has the main state that is relevant for this message. And then the database actually talks to the application and says, hey, okay, now I do have a message, and I do have all the state that is relevant context for processing this message, and call the application to handle this. So we're basically putting the database in charge of driving this. We're not letting the application react to the messages and let the database then handle the requests that the application issues, but we're letting the database do the requests to the application whenever it feels it's a good time to do that. So yeah, in some sense we're changing where the messaging, and with the messaging actually the main event loop of the application happens. Does it happen in the application, or does it actually happen in the database? And who's basically the, let's say, purely reactive part? Maybe it's not fair to say database is purely reactive. It is, of course, a lot of things also proactively in practice. But for the sake of this argument, for the handling of one request, usually the database reacts to what the application decides to do. And in this case, in the other scenario, we'll change this around. The application reacts to calls from the database. So in some sense, we would basically rewrite this architecture to saying we have our API gateway sending the events to the database, letting the database route this to the correct chart, invoking the application logic, and then the database communicates with another database, which can also again invoke the function. And when that communication actually fails, then it's really not the application's business, and there's a lot of very good things we can do to handle this and retry this with high consistency without the application ever having to worry about this. And we can immediately apply all the ideas that have come out of all these decades of research in distributed systems and databases. There are maybe a few core things that are critical to this observation. So first of all, the application logic, being a reactive part, would actually be, if you wish, would be basically a pure function in the functional programming sense, in the logical sense of a function that has no side effects. It only depends on its inputs, and the inputs in this case are, if the database invokes the function, let's say it gives the function the relevant rows that it's interested in. Let's assume our model in which we built the application has a way of informing that up front, and it can give the function the relevant messages. So any invocation of this function is pretty much idempotent. So failure handling is pretty easy here. We do need somehow a way to understand how messages and state fit together for this model to work, and we're going to see later that there's actually very, very common ideas how to do this. And once state updates and messaging happen in the same layer and are taken care of by the same system, it's actually straightforward to make them atomic. I mean, it doesn't come for free, but there are very well-known techniques how to do this. So yeah, once we have this problem of integrated state and messaging, there's all these solutions that have been around in research for a while, and I can in my words, in its core, what we basically need in order to solve this well is a distributed transaction log. If we take a slightly more high-level approach and say we don't want to build everything up from a distributed transaction log, then it's also quite similar to the work that stream processors have done for the last years, and that kind of brings us to the whole angle of Apache Flink as being one of the stream processing projects that have worked on making convenient abstractions for stateful processing of events. So this is what we've tried to do in this project, actually leverage that technology to solve that problem in a convenient way for users. And maybe before diving into exactly how stateful functions work, it makes sense to just take a brief look at Apache Flink. I'm not sure if everybody in the audience is familiar with the project. I would just quickly go through it and recap the most important bits. So in essence, the core, the foundation of Flink is this runtime that does stateful computations of the data stream. So consumes events, updates state, produces events, and does that in a consistent manner. And then there's various APIs, libraries, and so on built on top of that to expose that for different use cases. So there's stateful stream processing APIs that allow you to build applications based on streams, state, and time, with nice tools like tracking time progress in through data, dealing with consistent state without having to worry about the details. There's the streaming analytics side. There's a SQL engine on top of that can execute both on static data, basically like on a non-changing snapshot, but also over dynamic tables that change over time, in which case it basically works like a distributed materialized view engine. So as the input tables change, it basically computes changes to the output tables. And then there's the event-driven application side, which is what we're talking about today, stateful functions. So the core of Flink is a distributed data flow. So events come in through some system. Very often it's a message queue or a log, be that a classical message queue, ActiveMQ, SQS on Amazon, a log like Kafka, Kinesis, Pulsar or so. Or it could also just be a stream coming from files that are being read. And the events flow through this distributed data flow. There's some operations that can be stateful, and in the end, some events are produced as a stream. And the result stream, again, it can go into a file, it can go into a message queue, anything that consumes a stream. And the whole system is kind of built as in a way that persistence basically doesn't come in the streaming data flow itself. So whenever the streaming data flow, let's say, updates a state, that's a pure local operation, be that in memory or in a partially on disk LSM tree or so. And persistence is an asynchronous background operation that goes to some scalable storage. Very often it's something like S3 or Hadoop distributed file system or so. There's also one other component involved, something like Zookeeper, etcd, or console, which is really mainly something for leader election and to store one pointer. It's a component you can actually ignore. It's mainly for split brain protection and things like that. I think the important bit is that the processes of Apache Flink, they don't assume that any of the local disks are durable or so any of the writes succeed. The durability comes only through this asynchronous state persistence in the background. And let's dig a bit into that, because that's actually important also for the stateful function part. So the idea is is actually this idea of event sourcing and memory image. That's maybe the best analogy I found, where you have events coming in. Let's say they're persistent for a short time. You do update to your memory structures. You periodically do a snapshot of your memory structure that you store durably. And then if there's a crash, you basically restore the snapshot and replay the events since then. So it's actually not unlike what a database does. You restore the table from disk and then apply the remaining events from the transaction log that have not yet been materialized in the table. And yeah, so it pretty much does that for its structures as well. And the interesting part is, how do you do this for a distributed system? So this is where this distributed snapshot approach from Flink comes. It's something that is inspired by Chandy-Lamport snapshots, which is the general mechanism to draw a consistent snapshot of distributed processes. The algorithm that Flink actually uses does do some simplifications, because we are dealing mostly with asynchronous directed graphs. So there's ways to avoid, for example, snapshotting in-flight data, which is the majority of what makes the snapshots costly, by certain alignment phases, and just strictly separating the epochs and the input. The details of this are described in in a paper reference below. Yeah, the important parts are that there's this that Flink's snapshots are aligned. So basically, when all streams report that they have advanced to the next epoch to an operator, then this operator draws a snapshot and forwards the epoch to the next operator. There's also a way to actually do this if you don't have an acyclic directed graph. You can actually do this with a feedback loop. You just have to, let's say, pass the epoch markers in through the feedback loop as well, and record the difference between the initial epoch marker and the feedback epoch marker as a part of your state. This is all if you're familiar with snapshots and how they work in Chandy-Lamport. It's quite similar with a few, the tailored specializations for the common cases that Flink encounters. Yeah, there's some interesting property in building a system like that, to say we're not writing actually to a durable volume, but we're doing this snapshotting in the background, and that actually makes it quite flexible in the scale in which you use it. So the one of the largest installations of this is actually inside Alibaba for the Singles Day, which is their equivalent of Black Friday, where basically the entire country goes shopping, and where Flink, being responsible for a lot of the recommendation and logistics pipeline, is actually processing in fact billions of events per second in total. So it's scaled out to a very large scale. But at the same time, it's also quite feasible to put it on a simple embedded system. You have to play some tricks to make actually the JVM shrink. But the general architecture is actually fine with that, and the checkpointing interval and is configurable. The bandwidth that you need really depends only on the state. So for moderate event rates, checkpoints are incremental. It's actually quite okay. So you can actually shrink this to quite a low scale as well. So that's basically the foundation that we have there. Let me maybe go back a few steps. A distributed data flow that supports stateful operations and persists them asynchronously in the background. And maybe one important thing to mention is that a lot of the semantics that you get is basically like a group transaction. You pick a certain number of events out of the initial stream, you process them in the operators, you do changes to your state, you write them to the results stream, not yet committed. Then you draw a snapshot. It's typically an incremental snapshot that records the changes to the state. You also don't have to freeze the system to draw the snapshot. It happens asynchronously in the background because the epoch markers just flow with the stream. And once the snapshot is complete, you commit the output. So it's basically a group transaction of moving data from the input state update to the output. And instead of logging intermediate changes, you actually persist a snapshot of the diff. All right. So with that, let's actually look how we can use something like that for to actually simplify building distributed stateful applications. Now the first thing is how do we actually model applications in such a way that we can really exploit these properties that I talked about in the beginning, putting state and messaging together, make the applications purely reactive. And a big inspiration for that is actually from this paper. Probably the Pat Helland paper, this idea of let's not do distributed transactions, but instead use, let's say in my words, stateful event-driven entities. If I can sum up the paper in one sentence, I hope Pat Helland never hears that. He'll probably jump at me. But that's basically the idea that we took out of this. The whole way to build these applications is think of modeling stateful entities, event-driven entities. So every entity, let it be its own function, and with every entity, let's not thinking of something like there's one function for user, there's one function for inventory management, but there's let's say one virtual function instance in how you build the application for one specific user, let's say for Kim. There's one function for an inventory item for our socks and so on. So this is very close to this idea of virtual stateful actors actually. So having these functions in a very fine-grained manner and attaching state to them and allowing them to send each other messages. So the whole API that's basically in bare bones what the programming model is. You have some source of events, an event ingress. The events are routed to some functions. Functions deal with events, access their local state, modify their local state, and send events to other functions. And one important aspect is that we don't want to physically really maintain a function in memory, of course, all the time in this model. Because otherwise it would be very expensive. So I think you can think of this really as a bit of a stateful virtual actor system. It's very close to that with certain guarantees on state and messaging, namely that nobody else interferes with your state and that messages that you send they'll always arrive. So if you do an update to your state and return a message or send out a message, it will either succeed or fail atomically. And the persistence for this comes from basically a distributed snapshot of this application being drawn for you in the background by the system in which it executes. In this case, Apache Flink. So there's a lot of messages and state updates typically that get, if you wish, committed together in one action in this model here. So how do we actually map this on top of a streaming system? Because this is obviously not a directed acyclic graph, which is what Apache Flink and to the best of my knowledge, most of the stream processors that have been built actually support. And the answer for that is actually a quite simple trick in the end. If you wish, it goes back to for me the way I always think about it is going back to my first semester theoretical computer science class where we learned as soon as you have a while loop, you can basically execute any program because you can use that while loop to build an interpreter. Like as a theorem in theoretical computer science. And that's almost what we've actually done here. So we've basically built a loop into the program and basically run it as an interpreter. Like it's a distributed, it's almost like a distributed while loop, if you wish. So there's one function dispatcher that takes an event and looks at it and says, is that for me? If not, then it puts it in a channel into some feedback operator that puts it into another shard, which is the shard that this is addressed for, and then this one can actually interpret this event and say, okay, this is a function invocation, this is a state update, this is a scheduled message to be delivered later, and so on. So that's basically what is happening here. Like the stream processor is running basically as a loop to run as an interpreter for this program. So there was one start, and that actually gives you this this abstraction of saying, okay, we do have an API now where we deal with stateful entities and messages. We don't have to worry about messages getting lost anymore. But there's quite a high price that the first version had, and that is now we're basically, we've sort of clustered everything together. We've put actually the computation into the stream processor, which means there's the state management in the stream processor and the computation in one bit. And even though the state processor snapshots out to the distributed storage, if you actually want to rebalance that, it is a bit of an expensive operation, because like the local LSM tree, which gives you fast access to the state, it will have to be like reorganized if you scale this out. If you scale this in, if you start a new node, it will have to populate its local structures from the distributed storage and so on. So it's a somewhat expensive operation. So we've kind of paid the price that we lost the separation of compute and state here, and making everything, let's say, painfully stateful. So scaling is actually more expensive than it should be. But that's not really actually a must in this in this approach. So the second version of stateful functions, which is actually the default approach that the project is taking now, is actually invoking functions again through a remote service. So the stream processor pretty much only does event routing, correlating the event with the relevant state, and then doing remote invocations to the functions, and using a few things like pipelining, pooling, batching of invocations to make this more efficient. And that again gives us actually this nice property where the compute layer can be treated completely stateless, and all the stateful parts are handled inside the stream processor, and actually more stateful parts than in a usual database application, because we're handling also the messaging part here. And yeah, just to give one example where it shows it a bit more visually, what is happening. Whenever an event comes, this event usually this event needs to be addressed to one of these virtual entities. It's then, by the stream processor routed to the shard that owns this virtual entity. It picks up the state for this and invokes the function. And the important thing is for each entity, there's only one invocation possible at any point in time. If there's an invocation already happening, it basically puts it, if you wish, into the table and says, here's an enqueued message that you need to take a look at once your previous invocation is over. And outgoing messages are again routed to the shard that owns the state for the target entity. And then they're both together supplied to the target function, and the reply to a request is always the state update and the resulting message. And then this just enters the Flink data flow, and Flink makes sure that the message sending between the shards and the state updates that they're basically transactional, and the invocations of the functions, they're basically item potent, because the functions don't need anything else than the message and the state. So they can just be retried if they fail. So putting this all together, this is how a typical application built on this looks like. Just use this as an example here. Let's say Kafka for as a source for our ingress events, and yeah, you can also replace, if you wish, Kafka here with the Kafka ingress and egress with something like an API gateway where a request puts an event into the ingress and waits for an egress event to reply to the request. So this notion of making it, eventing is, you can switch between the event-driven approach and the request response approach, as long as you have a persistent buffer between the two. Yeah, so this is basically what this looks like, and yeah, maybe to point it out again, I think it's a fairly simple thing to do in the end, which actually gives some surprisingly good results. And the core, I think, lesson learned for us in this project was that something we initially didn't do during our work on stream processing is making sure we keep this separation between compute and state properly. But the thing that is different here is that messaging is handled in a different way, right? Messaging traditionally happens as part of the application layer, and in this approach, messaging happens as part of the state management layer. So in some sense, it happens as part of the database, and that's why for lack of a better name, I've sometimes called this like an event-driven database application also. So call this pattern of using the stream processor to do both messaging and state management together, like an event-driven database. Yeah. So this is actually let's say the main takeaways of this project, of what we've been doing there. There's a lot of similarity between these spaces of stream processing and event-driven applications. In some sense, stream processing is taking this event-driven reactive approach to a very specific extreme level with some constraints. These constraints usually being around, how can operators communicate with each other? How do they think about uptime and completeness and so on? But completeness of data. But there's, like, in general, a lot of the concepts are very similar, and it's a pretty neat thing to just take a stream processor with support for a loop and to turn it into an interpreter for distributed event-driven applications. When building distributed applications, it's a lot of things become very easy if you just have the state and the messaging more tightly integrated than what our architectures usually suggest us to do these days. And when doing that, we need to be careful how we handle the compute part. Like in the stream processing world, putting the compute strictly together with the state is both a blessing and a curse. It's a blessing because it gives you very high performance and efficiency, and it is a curse because it means you cannot really scale and administrate the compute part independent of the state part. So every update, every scaling operation becomes actually stateful. But it doesn't have to be this way. You can actually pull away the compute from the state again if you just leave the messaging part with the state. That's actually pretty much in a nutshell what stateful functions is. And I'm personally curious if this is an idea that's an idea that we're going to see more in the future. This idea of an event-driven database, because it seems to make too many things too easy to just ignore this. In some sense, what we've built here on top of Apache Flink is a prototype for something like this to be used. I think if you would build a completely event-driven database from the ground up, you could probably do a lot of things even more efficient than we're doing this today. That's pretty much it. Thank you for listening. And if you're interested in this space and you're looking for someone to collaborate with, please feel free to reach out to me. Thank you very much.
Thanks, Stephan, for this great talk. Do we have any questions for Stephan? You can just turn on your camera and unmute your mic, or you can, if you're a bit shy, you can just write a question on the chat or on the Q&A session on Zoom.
Stephan, Mohan here. Where would you put something like stored procedures in traditional databases in the context of something like this? And especially if the stored procedures, or maybe, what do you call them? In user-defined functions with a state that's maintained because you are trying to do user-defined aggregates, where as more operations happen, you are computing the incremental parts of the aggregates.
Yeah. I think this is a very good question. So, and in some sense, user-defined functions and triggers. I think if you think of this, you can almost think of it as an extreme way of combining user-defined functions and triggers. I mean, the whole stream processing thing. I think, I don't know. I think if I were at university, I would actually just try for fun to get one of these databases and just say like, how far can I actually get in building a stream processor by just using one table as as an input log, defining a trigger on it to call into some functions, update state, and so on. So, yeah, I mean, if you think about a system that's really designed to mainly do this, then I think you'll arrive at something like that.
If you look at how replication works, at least in the IBM Q replicator, where it reads the log and figures out what changed and then sticks it into a table if you want, because you can publish these events. And then on the other side, this is called the capture part. On the apply side, either these messages that go directly from the capture to the apply, or the apply part goes and reads those published tables where you might have published these things that you figured out by rummaging through the log as XML, whatever kind of documents. And then the apply part picks up either the directly arriving messages or these entries in these tables and goes and does the update on the replica.
Right. So I'm not 100% sure how well it would work if you say you have a completely distributed setup, like also like a shared nothing setup, not just replication or so, but also partitioning, and then you say one user defined function and a trigger which puts something in a table for a different for something that goes in a different chart, and I don't know, like this would make a few round trips and then go back and so on. Like how efficient would that work? But I think, yeah, and I mean, in some sense, you can think of that as, I think the whole stream processing space is a bit of an extreme form of doing that, like reacting to changes, like triggers, and then computing over state, like a UDF. Just really that as the first, as the main core construct, rather than thinking of the table as the main construct and this like bolted on top of. It's kind of, I would say it would do it the other way around.
Yeah.
And I think the other part is now assume that these user-defined functions, they don't need to really run in the database, because in the general case, the user-defined function might actually, it might invoke a machine learning model or so that takes half a second or so to run, and you don't want to like run this necessarily as part of your database kernel, because not sure what the threading model is, but let's say you don't want to block this thing by let's say external operations, right? So you would actually pull these user-defined functions out and let actually the database invoke them externally through a well-defined protocoler. So it's kind of the next step, right? And you would give the user-defined functions a very isolated scope that they can access, right? So they couldn't.
We already have that.
Arbitrary.
Yeah, this notion of fenced versus unfenced even stored procedures, right? In order to give more protection, even not run it within the DBMS.
Right. Okay, but yeah, I mean, think of this as a bit of an open protocol to do this, right? You don't have a fence procedure that executes next to the database process, but it's a fence procedure that can run behind, that has a standard invocation protocol that could even, be behind another load balancer or something like that. So that you would say, okay, I want to invoke 10 of these for these sets of keys because those are the triggers that currently fired. And then it just shoots to the load balancer, and then there can be something like a serverless platform behind that spins up a few containers because it detects that these things are actually blocking for a while, and then they execute, and then system that is actually built in order to pipeline these requests, make sure that one per primary key is happening and not more, and so on, and basically schedules them in a good way for such an architecture. So I think the mental model is right. Yeah,
thank you.
Just think of that as the core thing. Yeah. Maybe the other way that's interesting here is, I think the way that the invocation of the functions is actually a standardized thing through HTTP or gRPC. It's a little bit like ODBC or so in talking to the database, just the other way around. So you don't actually need something that's tightly integrated. It doesn't have to actually be, let's say, like vendor instance specific. You can almost think of this as a standard protocol, just for the other way around, for the database talking to the application rather than vice versa. So you don't need like a special SDK actually for the functions. There are some that make it easier to build these functions into the request handlers, but you can in theory put these functions behind any service that talks HTTP.
I mean, in the good old days, some of the database guys built these things where I've forgotten now what the terminology was for talking about them, where you are maintaining some state outside the database, and as the database state changes, they were recomputing this state that was being maintained outside. In a sense, like stream processing as the database guys defined, right? You have the standing queries, and as the database state changes, the results of these standing queries get pumped to the user who has some subscriber kind of motion.
Change data capture over the transaction log or something like that, or
no, even you want to get notified whenever some interesting change happens in the database, right? So these are these queries that are constantly running, and as new states appear in the database that are relevant for these queries, then they get figured out what was relevant about the state change, and then whoever issued these queries, standing queries, they get notified. This is like publish, subscribe, basically.
Right. I think that idea that you have is a bit closer to how I think the streaming SQL side on Flink offers, which is exactly building these standing queries. I mean, in some sense, that's what I tried to explain with this initial slide on Flink. If you do computation over streams with state, this is an extremely powerful paradigm where a lot of things kind of become variants of this. So standing SQL queries are a variant of this. Stateful functions here are a variant of this. It's different. Let's say different tooling built on top of the same core principle, just to serve different architectures and different use cases. So the core thing, I think distributed stateful streaming is this very powerful tool. And I personally think that it's kind of the complement to, I think the database architecture where you think putting information there first, and then compute on request or so. And in streaming, you say put a standing query there or standing stateful computation there, and compute on change. So kind of, I think with these two complements, you can build most things if you then put the different tooling for different scenarios on top. All right. There are other questions. That was good. It was also nice getting a Mohan question again, I think.
Welcome.
Do we have any more questions? It's funny that especially when we started this discussion with Mohan, it made me think about when I started working with research at the time. We were working a lot with scientific workflows and that model of CCA. And I remember that we had some problems for distributing the computation once the process would start. Can we have something similar with the function? For example, once once the events start to arrive, maybe because Flink is distributed, so maybe you can stress too much some part of the cluster and not other parts. So is there a way, I don't know, maybe to balance this computation, do something like that?
So I didn't get the last half of the sentence.
Is there a way to maybe sorry, microphone. Is there a way to maybe balance the computation to balance the computation on the cluster? You know, if you consider that it's you have part of the cluster that's being overused, lots of events arriving, and maybe you want to exploit better the cluster, the machine.
So, I mean, this model, and I think that's true for, let's say, for most of the approaches to stream processing, also is, I mean, it can basically parallelize well as long as there isn't one primary key that everything hits, right? Because every action is bound basically to one key, and per key they execute after another, right? I mean, especially in this stateful function models, as long as it doesn't hit the same key, even if it hits the same shard, it doesn't matter, because it basically implicitly rebalances between the shard that owns the state and the layer that does the compute through an API gateway or load balancer. So that case is actually much easier if you've written something that, you know, just hits a single key too often. Then yeah, there's no magic solution to that.
Yeah. All right. Well, so we can continue this discussion on Slack. I would like to thank you again, Stephan, for this great talk. And now let's move to our next tutorial, which is Delta Lake, which will be presented by Kate and Ima. Kate and Ima, you can already share your screen with us. And thank you again, Stephan.
Thank you as well.
Thank you, Stephan. Bye.
Bye-bye.
Hi, everybody. Hang on a second. I will get started. All right. Go ahead and share my screen. Hi, I'm Kate. I'm going to put some links in Slack that you guys can use. Is it okay if I pin this tweet temporarily just so folks joining can find it?
And hi, everyone. My name's Douglas. I will be just here to help answer some questions. I'm also a Databricks employee. So Kate, Emma, and I all work on the curriculum development team here at Databricks. And we're really excited to share some content on Delta Lake with you all today. Emma is having a couple of technical difficulties, so she'll be logging in shortly. Are folks using the Slack channel for these discussions, or are we mostly doing conversation here in the Google chat?
I think we are mainly using Slack for discussions that come after the tutorials, but I would say that for the other sessions, people were using more actually people, as we are not a lot of people, basically everyone was just opening the mic and asking the question directly. So it's being more like that. And Slack, we're reusing more for after the tutorial discussion. But,
okay, great.
Feel free to use Slack during the presentation. I think it's okay. Everyone has access to it. Anyway.
Okay, and I just went ahead and shared those same links here into the Zoom chat as well. You don't need to click these links, but this will allow you to actually follow along with this workshop using the Databricks Community Edition. And I believe Kate is going to take you through the process of setting all that up. So if you want to go through the process of actually importing these notebooks and running some of the code, then we'll be able to do that. Before we get started, are there any questions on Databricks or Delta that I can answer for anyone? Okay, great. I'll let Kate take it away.
Okay, thanks a lot. So today we're going to be talking about simplifying and scaling data engineering pipelines with Delta Lake. We'll all be here and we'll be